you remember one of the questions that we had at the beginning was, why is it worth doing this kind of thing? Why are we spending all this money and resources doing this? And one of the reasons is it is incredible training for people, right? So we learn and we can develop skills in this way that can be widely applicable in other areas. And so you'll see a vivid example of that in the next, in Jamie's guest lecture. So he's a guy that really grew up in this business and is now applying it in something that's very different. And so I think that will be a lot of fun. It's too bad I'm missing it. But I'm sure that will be great. Okay, so let's move to this lecture. So and actually, even with this lecture, I want to start with something that's not, just going back to things that I said in an earlier lecture. So I've been talking to a lot of people before the lectures, and I'm getting a lot of grief actually about some of the stuff that I said in the first lecture. So I had showed diagrams that look like this and made bold claims that all of everything around us is totally explained by basic physical principles. And so I want to, I'm standing behind this claim, and this is sort of my act for Stand Up for Science, right? So we stand up for Science Day, so this is my me taking a stance. So I decided that we'll go through examples of the kind of reasoning I have in mind here. So this is we'll really put teeth behind these qualitative, sort of fuzzy statements that I said in the first lecture. And it's really a powerful way of thinking about the world and estimating basically anything to within an order of magnitude. It's also fun, and believe it or not, this is something that I actually do a lot when I'm on airplanes or in free time, and it's easy. So, but we'll go through this now. So the idea is, and so the other thing is, if some of this stuff goes by too quickly, or you don't understand exactly what's happening, it won't be related to the rest of the lectures here. Okay, so what we'll do is use something that's called dimensional analysis. And this is something that isn't really taught. I really think we should be teaching this to even high school students. But it's something that we don't teach much even in college. But the idea is that you put in the right physics, okay, and you try to get the answers to within geometric factors. And I'll explain what that means. But basically, you don't really care that you get the precise answer. You care that you get an estimate that's within a factor of 2 pi, 10, 30 even. So something that's definitely not right in detail, but gives you a right feeling for the scale of the problem. And so we're not going to worry about any of these 2 pi's, etc. And so we use this squiggle. Okay, so the squiggle means not equal to. It means roughly equal to or within a factor of 10, 30, etc. Okay, and it's called dimensional analysis because that's really, you're putting in the correct dimensions, you're putting in the correct physics. And so I'll show examples of this. It's pretty simple. So if you want to estimate the volume of something or how much space something takes up, you just say it's whatever the size is raised to the third. Okay. And so for a cube, a good estimate of the size. So something that's really three-dimensional. It's not really skinny like a line, or it's not flat like a sheet, but it's like I would be a volume. So you could take some measure of the size and just cube it, right? And so for a cube, this actually works exactly, right? So if you take a good measure of the length of a cube is just the length of the side, and you cube that, you get the exact answer. For a sphere, of course, it's more complicated, but a good measure or a measure of the length of the sphere is its radius. So with dimensional analysis, we would just say, well, the volume is the radius cubed. Now, of course, that's not right because there's really this 4/3 pi here. But that comes out to 4.2, which is roughly to within our squiggle equal to the radius cubed. Okay, so this is the kind of thing that we're not going to worry that this is a 4.2. For a sphere, there's another. You can also say, well, I'll just take the diameter, and that also works just as well. So the diameter, you can say it's the diameter cubed. Now these give different results, but they're the same to within our squiggle. And so the squiggle covers that. And then another example is a cylinder. So if there's something that's it's not really a sphere, right? We're just going to say it's whatever as long as all the dimensions are roughly the same, we'll just say that it's that cubed. Okay. If we had a cylinder that was really skinny and long and narrow, and there were really 2 scales, then we would use the small scale squared times the big scale. Okay, but it's this kind of thing where we're not going to worry about the details too much. We're just trying to get the right scaling for how the object would change. Okay, so another example is the kinematic energy, or kinetic energy is 1/2 mv squared. That's just going to be mv squared. And I've actually been doing this, some of you I'm sure have caught on to this, but so I've been writing this uncertainty principle like this. It's the uncertainty in Px that's bigger than h. Really there's a factor of 4 pi here if we were going to care in detail. I've been leaving that off, so we'll continue to do that. Okay, so now we need some units to work in, and units are something that I really dislike, okay? And really all numbers are unitless, okay? So when someone says something is like 2 meters, what they really mean is there's this bar that's in Paris, and if you get the bar and you put it up to it, it will go to it twice. Okay? So that's really what they mean. So all numbers in the end are really unitless, and the units that we assign to them really tell us more about human nature and the history of things than really about the fundamental physics. So what we're going to do is try to get around that as much as possible, and we'll work in what's called natural units. Okay, and again, this is something that some of you may have heard of, but it's not taught as well as I think it should be. Okay, and so natural units are really the correct way, I think, to think about the world. Okay, this is how physicists often think, and I think this is really what makes them seem smarter than other people. Is they think in these terms, but it's actually very easy. Okay, it's much easier than worrying about metric, British, MKS systems, with all these conversion factors. And so the idea here is instead of using standards that are in Paris, like the bar, this whatever bar it is, or this kilogram, we're going to use the standards that are set by basic physical principles. Okay, this has the advantage that the numbers have direct physical interpretation. Okay, and it'll be clear what this means in a second. Okay, so in natural units, what we do is we take these things that are the fundamental constants and we set them equal to 1. So the first example is the speed of light. So we just say that the speed of light is 1, the number 1. Now the speed of light it conventionally has units of distance over time. So if we set this equals to 1, that means in these natural units, the distance and time will have the same unit. Okay? And that makes our equals mc squared easier because c is 1, which equals m. And actually, this is something that they're already familiar with, right? So when someone says, how far is it? What they're asking is, what's the distance between here and there? And if you reply with, it's about an hour from here, that's something that can make sense to you. But really, this is a time, right? And so what they're saying is if you travel in a car at roughly the speed limit, it'll take you an hour to travel that distance. And so it's really the same thing. So when someone says, how far is it away? It's a light year. That means it takes something that's really going at a constant speed a year to get there. Okay, so this is one that you're already familiar with. One that you're less familiar with is this other constant from quantum mechanics, this h. So we'll set that equal to 1 as well. And h has units of energy times time. So that means energy has inverse units to time because this combination is unitless. And it's also energy and distance are inversely related. Okay, so this means when we set this equal to 1, this means that we can now trade energy or mass, because they're the same now, for distance or time. Okay, so there's really only one. There's only one thing. There's all one unit, right? So we'll work in units where everything is in terms of energy. Okay, and for energy, we'll use a GeV as our base unit. I mean, again, all these numbers are unitless. We'll use a GeV, which is nice because it's about the mass of a proton. So we'll compare everything to the size of a proton. Okay, so we'll do everything in terms of GeV, and we need conversions to get back to the everyday units, so the human scale units, and here they are. So we only need 3 of them for almost everything we'll do. A GeV is 10 to the minus 27 kilograms, so an incredibly tiny amount of weight in GeV. An inverse GeV, that's like a distance, and that's also an incredibly small distance, so it's 10 to the minus 16 meters. And then a GeV inverse also has the same units, because these have this space and time have the same units. This is also a tiny time, so 10 to the minus 25 seconds. Okay, so now this seems crazy to use this. Why would we use this? So here's some examples. So a proton weight is about a GeV. That's why we picked the unit. A proton size has units of distance, okay, and that is 1 over GeV. So a proton size is like 1 over GeV. Okay, so these are sort of baked in from the beginning. Now let's go to more exotic things. So my height, so I'm about 1 meter, okay, up to within the squiggle, and from our conversion, that's 10 to the 16 inverse GeV. Okay, so that seems like a funny way of describing my height. And my weight, I'm about 100 kilograms within the squiggle, and that's 10 to the 29 GeV. Okay, so why are these units better? Well, you can see immediately from this that I'm as tall as if you would put 10 to the 16 protons on end, right? If you stack them up, that's how high you would get my height. Okay, so this is my claim is a much better way of doing it than putting this random bar in Paris, right? You don't have to know about the bar in Paris. You know. So an alien, for instance, we could tell them that this is my height, and they would understand. They would understand what I'm talking about without having to go to Paris. And then my weight, you can see even more explicitly. This is just saying that I am made of 10 to the 29 protons. And so immediately, just by knowing what my weight is in this correct unit, you know something fundamental about me. Okay? I'm made of mostly protons, and this is how many. This number is how many that I'm made of. Okay, so those are some examples. So now let's move to the forces that dictate our everyday life. So the first one we'll talk about is electromagnetic energy. So this is just the one inverse square law. So now we can look at what the units of this of how this works. So energy has units of energy. So that's just the GeV. And on this side, this has units of distance, 1 over r. So 1 over distance also has units of energy. So that's a GeV. So whatever this thing is here, it's just got to be a number. Right? It can't have units because the units already match just with these two terms. So indeed, this is a pure number. This is the number that we saw in the previous lecture. It's a small number. It's about 1 over 137. So this is interesting. There's a small pure number that's associated with the electromagnetic force. If we think about the gravitational interaction, it's also an inverse square law, so we get a very similar starting formula. Energy is units of energy. But now if we look at what's on the right-hand side, this thing has units of 1 over energy, but a mass is a unit of the energy. So this combination here has units of GeV to the third. Okay, so that means that whatever is sitting here can't be a dimensionless number. It has to have units. And it has to have units of 1 over mass squared, because it has to cancel this guy. So really, so this G Newton is a dimension-full number, and the way to get a dimensionless number out of it is to multiply by some mass squared. So in our example here, where we just have 2 protons separated by a distance, the thing that's dimensionless is the combination of this constant times the mass of the proton squared. And an interesting thing to note is that this is an incredibly small number. Okay? So it's 10 to the minus 39. Right, so that's 0.00 with 39 zeros and then a 1. So it's shockingly, in many ways, small. It's, and this is the thing that really you should compare with this 1 over 37. So you can see that gravity is incredibly weaker in this real sense. And this is why it's so irrelevant for the stuff that we talked about. We'll talk about it in particle physics. Okay, so my claim is that essentially everything around us in our everyday lives we can boil down to combinations of these 4 basic numbers: mass of the proton, mass of the electron. Okay, it's about electron's 1,000 times lighter than proton. This alpha number that measures the strength of the electromagnetic interaction. That's 1 over 37, or to the squiggle, it's 10 to the minus 2. And then a number that I'll call alpha G. It's kind of like the gravitational strength, but remember, it's this combination of dimension-full parameters, and that's 10 to the minus 39. Okay, so my claim is that everything around us is just really a combination of these numbers, and we'll work through some quick examples of this. Okay, so starting with one that we've already seen, actually, in the second lecture, is atoms. So this was the energy associated with an atom. There was this potential part and a kinetic part, and this was the big mystery before quantum mechanics. It looked like it was unbounded. But quantum mechanics has this uncertainty principle that kicks in. Before this was an H, now this is going to 1 in our natural units. And that allows us to substitute this p squared with the 1 over r squared. And this was the thing that had these two terms and that now canceled, and there was a minimum when these things were roughly equal. Okay, and this provided the stability of matter. And now we can actually solve for what this is. So we can require that these two be the same order of magnitude, and this is the answer you get. Okay, so you get 1 over the z is the number of protons, say, in the atom, alpha times the mass of the electron. Okay, and we can see sort of how accurate this is. So this, if you just put in this combination, this gives you a prediction of 10 to the minus 11 meters for hydrogen. The actual value is 2.5 times 10 to the minus 11, so it's not, not so bad. It's certainly within our squiggle that's saying trust me to a factor of 10. If you go to atoms that have 10 protons, you predict 10 to the minus 12. Again, not so far off. It's 4 times 10 to the minus 11. Now, actually, as you get to larger and larger numbers of protons, there's also larger and larger numbers of electrons, and those electrons also start contributing to the effective charge, and that's something we didn't account for here. So there's some screening that's possible. So it gets the prediction. This simplistic thing starts breaking down for when you have more than 10 protons. Okay, so we predict 10 to the minus 12, and it's actually more like 10 to the minus 10. And so we could put in the details of the screening to get this number, but for here we're not going to worry about that again. And we'll just say if we're looking at an atom that has Z higher than 10, we'll just use 10 to the minus 10. So it's a roughly constant above 10. Okay, so that was for the radius of the atom. The nucleus goes like 1 over the proton. That's the size of the proton, and a factor that's related to how many protons you have. And now you can ask, well, how do these compare? So we'll take the ratio of those two. This is the ratio of the nucleus to the size of an atom. And that is a number that goes like alpha, okay, which is 10 to the minus 2, times the ratio of the electron to the proton mass. That's 10 to the minus 3. So this is, combined, is 10 to the minus 5. Okay, and this confirms my statement that, well, an atom is mostly made up in terms of volume of the electron. And you can see now we can put a number to that. It's 10,000 times more atom or more electron than nucleus. Okay, so we can also calculate other things. So now that we know this radius of the atom, we can use this formula again to calculate what the momentum is of the electron. Okay, and so it's just 1 over. It's related by 1 over the radius of the atom. And so I'll write it in this form. So this is the mass times the velocity. So the velocity of the electron within an atom goes like z alpha. Okay, now this is also incredibly interesting, right? For the first thing is that this number, remember, can't be bigger than 1, because 1 is the speed of light. So that immediately tells you that the number of different atoms you can have is like 1 over alpha. Okay, and actually, if you look at the periodic table, there's about 1 over alpha atoms. And the physics behind that is if you have more than, so why can't you have an atom that has 300 protons? And the idea would be that the electron would be moving so fast there that it would start exciting the vacuum, right? It would start creating, the electron itself would have so much energy that it would be unstable, and it would excite the vacuum. It would create pairs of electron-positron pairs, and it would lose energy. Okay, and we're seeing that reflected in the fact that there's a upper limit here. Another interesting thing is that when Z is 1, you have hydrogen. That was the atom that we studied first in quantum mechanics. And this is why that we could do quantum mechanics without knowing about QFT and about worrying about relativity. And that's because when this is 1, the speed is 10 to the minus 2, so it's moving relatively slowly compared to the speed of light. And so the effects of relativity aren't that important. And so just regular old quantum mechanics can describe the hydrogen atom. Another thing that comes out immediately from this simple equation is why electricity is much more important than magnetism. So you boil it down, magnetism is really, essentially all the effects of magnetism come from the fact that the electron is moving within atoms. And you can see that it's moving relatively slowly. It's moving like a factor of alpha, which is 10 to the minus 2. So this is why, in everyday materials, the electrical forces tend to be stronger than magnetism. Okay, some other things we can do is put in the energy. So now we know the momentum. We can use either of these terms to give an estimate of that, and that's what you see here. Interestingly, this goes like the mass of the electron times alpha squared z squared. Okay, this is another number that we can easily check. We can put in our conversion factors for GeV here. And from many of you that have taken quantum mechanics, you know that the hydrogen atom has this famous 13.6 eV binding energy. And if you put in our, with our rough estimate here, we get something that's like 50 eV. So again, this sets the scale of the accuracy at which we're working. Okay, so this is about atoms. And I just want to highlight the point, this will come up later, that it's, so for atoms, it's the electron mass that's king. Right? The electron mass is dominating the energy, it's dominating the radius, etc. And the proton mass really doesn't make an appearance at the scale of atoms. The proton is really just sitting there, and it's the electron that's running around doing all the work. Okay, so now let's move on to solids. So to a rough approximation, certainly within our squiggle, a solid is nothing but a bunch of atoms packed right on top of each other. And now we can ask questions about the solid. So one of them is, what is the mass density of the solid? Okay, mass density has units of the mass, so what's the mass of an atom? This is where a proton comes in. Most of the mass is in the proton, and then divided by the volume of the atom. Okay, and so that's what you see here. So this is the mass goes like Z times the number of protons times the mass of the proton divided by this radius of the atom that we've just calculated. Okay, so we get this combination of these parameters. You can also ask what's the pressure of a solid. Okay, so pressure of the solid is something that's like force per area, or you can think of it as energy per volume. And this is kind of like the energy, if you wanted to break the solid or crush the solid, this is how much energy you would have to put in. And that goes like the energy of the atom divided by the radius of the atom. Okay, so that's the energy per volume. And that gives you, so here, this is the energy of the atom that we just calculated, and we already know what the radius is. So that goes like this combination. And with these two numbers, you can also ask various questions. So something that you might remember from classical physics is you can estimate the speed of sound on like a string, the speed of a wave on a string, or on solid as the ratio of these two numbers. So it's the ratio of the energy density to the mass density with the square root. So that's this formula. If you don't remember, don't worry about it. But now we could put these in. Okay, we could put these numbers in, take the square root, and we would predict 25,000 meters per second for the speed of sound in a solid. And you can see that it's not bad. So there's, they measure these. I don't know how they measure these actually, but I looked this up online, and it's close. Okay, so it's certainly within factors of 10 to 30. Okay, so this is working for solids. Now let's move even bigger. So we'll ask these questions for planets. So what is a planet? It's basically a big solid where the pressure of the atom that we just worked out is balanced by the gravitational pressure. So you have gravity wants to crush everything, and you get a planet when the mass of the solid resists that pressure. Okay, and so what's the gravitational energy? So the gravitational energy is just the inverse square law, but now for the planet itself. So it has this Newton's constant times the mass. This is the mass of the proton. This is capital N, which is the mass of the planet, squared divided by the radius of the planet. And so you can ask what's the gravitational pressure, and that again has units of energy over volume. But now the relevant quantities are the gravitational energy and the volume of the planet. So the volume of the planet is the radius of the planet cubed. So this goes like a fourth in the denominator here. It's just this number with a 4. Okay, now what's the mass of the planet? Well, we just said the planet is just a solid, so it's the mass density that we calculated, so the mass per unit volume times the volume in the planet. So this is a number that we know, and it's written here, so this just goes just like the radius of the planet squared times this number that we just looked at. And now we can solve for this pressure, right? So we can put in this expression in for this mass of the planet, and you get this combination of things. And now to solve for the radius of the planet, we can demand that these two are roughly the same, so that the pressures are balancing one another. Okay, this gravitational pressure is the one we just worked out. This pressure for the solid is on the last page. Okay, and that's the expression there. And this gives, we can solve this for the radius of the planet. And here it is, so it's these combinations of numbers, but I wrote it in a way that I think is really interesting. If the radius of the planet, or the size of the planet, is the same as the size of an atom, times this factor, and this factor is the ratio of the strength of the electromagnetic force to the gravitational interaction. So really, you would expect the planet to be the same size as an atom, scaled by the relative strengths of these two interactions. Okay, so I think this is really really remarkable. Let's see, that's basically what I said here. But this is why things are big, right? If you think about it, it seems like all the fundamental forces are operating on very, very small distances, right? So that it's always 10 to the minus 16, 10 to the minus 27, and so it could be strange that we have such big things and big things moving around. And here you see it totally explicitly. The radius of the atom, this is something that's microscopic. It's governed by those laws at that scale, but it's increased by this factor here, and you have this incredibly small gravitational number that's really blowing up, and that's why we have big objects. Okay, and I'll do so we can compare predictions again. So you take this naive estimate, that gives you about 10 million meters. The actual Earth is 6.4, so not so bad. 6.4 million. You could predict the mass. This should be mass of the planet. That is 10 to the 25, and that's also not so far off. So it's not exact, and often in university we really worry about getting these numbers exacted. So you don't see these calculations where you just put in the simple scaling. But if you only care about this accuracy, then this is definitely the way to go. Okay, and then the last really the last example that I'll do is to put an estimate on life. Okay, so this is the thing that started this controversy. So we can put limits on the size of life, and there's a number of different ways you can think about doing this, and they all roughly give the same answer. The one that I'll take is I'll say, well, life is made of solid, so we have skeletons. They're just solid, and of course that's not right in detail, but within our squiggle that will work. And it would be that, and life is something that moves around and falls a lot, and we don't want it to break bones when we fall. Okay, so that will be the constraint we put in. So if it breaks bones when we fall, that's bad for life, and it probably wouldn't survive. So now let's estimate how much energy you lose when you fall. Okay, so the estimate, the energy associated with falling goes like the mass of the animal times the gravity, the local gravity of the planet, times how far the animal's falling. So this is like mgh, if that means anything to you. And we can do this. Okay, so the local gravity of the planet is just this constant times the mass of the planet over the radius of the planet squared. But now we know the radius of the planet, mass of the planet in terms of these fundamental parameters, and that's the combination that you get. And again, there's no fancy math here, right? It's not we're not doing any integrals. There's no it's all just algebra. Okay, so if you would put this in, you would predict that the acceleration on the surface of the planet is like 5 meters per second, and on Earth it's 9.8, so it's not too bad. Okay, so now the other thing that we have to estimate is the energy associated with breaking a bone. Okay, again, you can make this as complicated as you like. What I'll say is the energy associated with breaking a bone is it goes like the number of atoms that have to be broken times the energy of an atom. And now, if you think about when you break a bone, you're not really crushing the whole skeleton, right? That would be if we took all the atoms in the animal and asked for that energy, that would be like compacting the animal in a crusher. But when you break a bone, it's really along cross sections, right? So you break all the atoms, along the cross section of its leg or something. And so this is the number of atoms associated with the cross section we'll put in. So if the animal's if you think of the animal as a giant sphere, it's the number of atoms along the cut of that sphere. Okay, and that's just shown here. It's the length of the animal divided by the radius of an atom. That's how many atoms are along one dimension, and you square that to get the cross section. And we already know we know the energy of the atom from the first thing. So you can estimate how much this energy. And then we say that there's a limit when these energies are roughly comparable. And this, putting this in, works out the size of the animal. Right? So now the size of the animal, again, is it's directly related to the size of an atom, but it has this coefficient that goes like the relative strength of gravity to electromagnetism. Now it's to the fourth power instead of squared. And similarly, you can estimate what the mass of the animal would be that lives on this planet, and that would be in terms of the mass of the atom with this other factor that goes like the 3/4. So again, you really see directly that the fact that we're big and we live on big planets is a direct consequence of the relative size of these interactions. Okay, if you put these numbers in, it's not so far off. It's about 10 centimeters. Of course, if you think about the physics, animals aren't just solids. They have protection. They have some liquid in there that can absorb some of this energy, etc. But it's not so, within a factor of 30, certainly this is not bad. The mass is also pretty good. It's about 100 kilograms. So really, all of the fundamental, and this is all, and these parameters, as we'll see, come from fundamental physics, and it's really dictating the gross features of what everything around us could possibly look like, right? Of course, this won't predict that I'm 2 meters tall versus a meter tall, but this is why I'm not 100 meters tall or 200 meters tall. So there's really, there's no bullshit constraints here from physics coming in these higher level systems.
Can I give you one caveat? I used to do dinosaurs at the Field Museum, so subject matter expert.
Yeah.
Every time they try to get limits to how big a dinosaur can grow, especially the four-legged quadruped, then they find something 2 or 3 times as big.
Right. Yeah. So dinosaurs, it doesn't actually work for dinosaurs. A lot bigger than this, but there's a lot of research, and I'm not familiar with this, that say that dinosaurs are probably the biggest you can get, and they went extinct, right? And so it's not.
They've been on Earth for 150 million years.
Yeah. There's caveats here for sure, but this is a rough. The dinosaurs could be 100 times bigger than they were. Okay, so that's the end of this thing. So that's really, trying to put, that's what I really had in mind when I was drawing these diagrams. But now we'll move to the topic of today's lecture, and that's the importance of the Higgs. Okay, so now there's more sources here. The Higgs is complicated. This is one of the hardest lectures I had putting together. Another reason why I wanted to do that interlude. But these guys are all, know this stuff very deeply. Okay, so last time in the standard model, we talked about what's actually in the world. So the standard model is a description of the fundamental constituents of the universe and their interactions. It's really a triumph of the 20th century. It combines our principles of quantum mechanics and relativity. It constitutes matter particles, so things that make up the stuff in the world. These are leptons and quarks. And there's three generations of these for reasons we don't know. And we also have interactions. Okay, these are the 4 fundamental forces. Associated with each of these, there's a particle that mediates that force. And I ended by saying that this is all consistent and wonderful, provided that everything is massless. Okay, that all these guys are massless, and these guys are massless. And this is a big problem because we know that they have mass. Okay. And so today's lecture is the importance of the Higgs. And you'll often see things written in the newspaper that say, well, the Higgs boson, or the God particle, is responsible for all the mass in the universe. Okay, so we're going to try to make some sense of this statement. Okay, so what's the problem with mass, actually? Why can't these things have mass? So it all goes back to this notion of spin. Okay, and this was something that was, remember, forced on us by this union. Okay, so matter particles have spin 1/2. Okay, they're fermions. And so quantum mechanics tells us that this is one of the things that's quantized, the spin. So there's only 2 ways that these things can spin. And so we say that they're either right-handed or left-handed. Okay, and so by that I mean, let's take an electron. If it's moving in this direction, the spin can look like this. So it's kind of like a right hand. If you put your right hands in the direction of this arrow, then your thumb goes in the direction of the motion. That's something that we call a right-handed electron. And then there's the left-handed electron. Okay, so that's just the opposite. So it's like using your left hand. So you can think of it as like if this was spinning in this direction, but it was moving that way, you would get a left-handed guy. Okay, so there's two kinds of electrons that can exist. And quantum mechanics, or quantum field theory really, tells us that massive particles can flip back and forth. Okay, so if I have an electron, there's some probability that it's like this, and then it can flip. Okay, so here's that shown here. This is an electron moving in time, and there could be these red guys that are right-handed, and it can flip to left-handed and back and forth if it has a mass. Okay, and really this is, the size of the mass sets the rate of the probability for flipping, right? So the heavier particles flip more often. Particle that's very light almost never flips, and massless particles never flip. Okay, instead of drawing those circles, I'll just draw it like this. These arrows represent the spin. So right-handed is in the direction that the electron is moving, and these blue arrows will be the left-handed guys. Okay, so what's the problem? The problem comes in when you think about charge. So electrons have charge, okay, and that means they take place in this, they participate in this interaction. Okay, they can emit a photon because it's charged. The electron is charged. It has a different kind of charge that we call hypercharge, but it's analogous to this, and that's why it can emit a Z, okay, because it has a hypercharge. But it's really the same idea, just different interaction. Okay, now the crazy part. This is something that you wouldn't believe if I just told you, and no physicist would believe this. But this is the way the standard model works. Is that left-handed particles have hypercharge 1, and right-handed particles have hypercharge 0. Okay, so there's this asymmetry between left-handed and right-handed charges. This is something that no one thought that this was possible. It was discovered. It was shocking. Many people got Nobel Prizes for it, but it's true. Okay, and this is the part that leads to contradiction. So it's only left-handed particles have hypercharge, and so this plus particle masses, immediately you're doomed, right? Because now here I have a massive guy that's flipping back and forth. Okay, but now if you ask what its charge is, its charge goes from 0 to 1, 0 to 1, 0 to 1. Okay, now we're dead, because on one hand, this quantum field theory tells us that massive particles have to flip back and forth. The standard model says that our actual universe says that these have different charges, so that means the charge, this hypercharge, cannot be conserved. But remember, one of the basic things that combining these quantum mechanics and relativity taught us is that charge must be conserved. Okay, so now we have a contradiction. Okay, and so we can get around this not with the Higgs boson, but with the Higgs field. Okay, so now I want to say a few things about what a field are. This is the first time we talked about fields. It's basically a mapping or a set of numbers to every point in space. Okay, and so you're actually familiar with fields already. So there's things like a temperature map. Okay, so this is like the temperature at every point in space. That's a field. Okay, the field is just a mathematical way of saying that. And there's more complicated ones. So there could be a wind map. So the direction of the wind at every point in space. That's kind of like an arrow or just a pair of numbers at each location. So they're not really complicated things. There's other fields in physics that we deal with, like the electromagnetic field, the gravitational field, but they're also very similar to this. Okay, and now typically most fields cost energy for being on. Okay, so if you think of an electric field, if you're going to make an electric field in this room, you would have to turn on a battery somewhere to set a charge on one wall and charge on the other. Okay, so that would cost energy, and so the way that we draw that is like this. So this is the field value, or how much if the field is on or not. And if the field is on, that costs energy, so this increases. And of course, if you have an electric field that points in that direction or that direction, it's also going to cost energy, and so it doesn't matter which way you go. Okay, so I'm going to warm up, but before talking about how the Higgs field works and gives particle masses, I'll just show a simpler example of how a field can give anything a mass, so a simple particle mass. And so we'll start with water molecules. So water molecules are little dipoles. So they're neutral overall, but they have there's more positive charge on one end than the other. So you can think of them as little arrows sitting here, where there's an imbalance of charge within the water molecule. And so to mimic quantum mechanics, we'll say that we're only going to consider two types of water molecules: up water, where it's pointed like this, or down water, where it's pointed in the other direction. Okay, so we'll only think about these two kinds. And of course, the masses of these are the same, right? All I've done is turn one upside down. And the fancy way that physicists say that is that space is symmetric. So it doesn't matter if you tilt your head one way or the other, you'll get the same mass there. Okay, now we'll break the symmetry by creating a field that points in a particular direction. Okay, so now space will no longer be symmetric. So I'll have some battery here with some charged plates. I'll put charge on this, and this gives an electric field pointing in this direction. So now, in fact, these have different energies because they have different charge distributions. And it turns out that the down water has more energy stored in it. Right? It really wants to flip up because of this electric charge. And if we hold it there, then we're putting energy into it. Okay, but remember that we have to turn on this battery to turn this field on. Okay, and that's really, but it's this field that's giving this potential energy, and that energy is equivalent to mass. Right, and so that's a way that an external field can give energy to a particle that's not moving, that can be interpreted as mass. Okay, so that's what I'm saying. Now down water has more energy or more mass than up water. And this is just one example of how a field can give energy or mass to a particle. And now I want to say a few things here. You'll often read about the Higgs field that it's like some kind of molasses that particles are moving to and bumping up against. But that's really not right. Okay, that's really that's not the way to think about it. Right. In this case, there's no net force of this field on the water molecule. Right. The water molecule is neutral, so it's not bumping into anything. If you push this water molecule in this direction, it's not bumping into any molasses or anything. So it's really not like the Higgs field is also like this. It's not like getting stuck in something like this. It's really the field is giving it energy, but it's not impeding its motion in any way. Okay, so now of course we're more sophisticated, and we know that these forces are mediated by particles. So really, instead of an electric field here, we should really think of this as being a sea of photons. Okay, so there's these charged plates are constantly producing photons that can travel between these two plates, and it's those photons that mediate that electric force. So that's what I said here. And so from the point of view of the water molecule, if you don't worry about these plates, or you make the plates very far away, it looks like it's just living in a place where there's constantly photons everywhere around it, right? And it's actually it can emit a photon or absorb a photon into the background electric field without really changing anything. So it interacts with these photons, and that doesn't really change the field within here. Okay? If the field is much stronger and these plates are farther apart. Okay? So in terms of the water molecule, it thinks that it's living in a space or a vacuum that's just filled with what we call a condensate of photons. So condensate is another fancy physics word, and that just means that there's so many photons here that you can remove them and add them without really changing anything. You don't affect the background from these charged plates. Okay, and the way that we draw this is we say here's our down water molecule moving, and it's experiencing this force, right? And that's interacting with photons, and these photons we just put little X's here, and that means they get absorbed by this vacuum. Okay, they're added or removed to the background vacuum, and that doesn't really change anything, so we don't have to really follow those photons. So we just put an X there. Okay, so in this example, we have these electric fields that have generated a condensate of photons. That's really the same statement. It's the electric field, and this is created by the battery, right? So we need to provide this power to turn this field on. Okay, so the Higgs works in the same way. Okay, it's the same concept, but we need to turn the Higgs field on. Okay, so for the Higgs field, we don't use batteries or charged plates. Instead, we use a trick. It's really, this is what it is. It's a mathematical trick that has a fancy name, but it's just shown here. So instead of drawing the energy like we did before, just a curve that goes up from 0, we say the Higgs field has an energy that has a shape that looks like this. Okay, and having this shape is referred to as spontaneous symmetry breaking. And the idea here is that the Higgs, it costs energy, or it's a non-zero, it's a higher energy to be at 0 field than it is to live here, say, okay, or here, right? These have lower energy. But in this configuration, the Higgs field is on, right? It has a non-zero field value. Okay, so the 0 field, where it would be Higgs field off, costs energy to be there. So it naturally wants to be here. So this is what we say, right? So we say that in the standard model, there is this field. Okay, this field has this shape, and that's enough to turn the Higgs field on. So it doesn't really cost us energy. We just have to dictate that this shape is the energy of the Higgs field. Okay, and I mentioned that there was a number of places where we had inputs to the theory, right? We said that we had to measure these masses, we had to measure the forces. This is another example, right? We have to say, oh yeah, there's this Higgs field, it has this shape, and that shape is an input to the theory. Okay? The theory does not predict what the shape is. And so it turns out it takes two numbers to describe this. But these are input to the theory. Okay, and so just like before, now that the Higgs field is on, this really forms a condensate of not photons, but something that I'll call V condensate, okay, V particles. And this works exactly like in our water molecule example. Okay, we'll see that in the next slide. Okay, and this is actually, there's a lot of beautiful physics that's related to generating this condensate that I'm not going to talk about. It's really a quantum mechanical effect that's related to the shape of the potential, and it's really the same thing that's happening in like superconductivity, if you're familiar with that. But you can think of it just like this. It's the Higgs field is on because of this shape, and the Higgs field being on creates a condensate, okay, or a field in empty space. Okay, so one question is, does all mass come from this Higgs field? The answer to that is definitely no. So here's an example. Okay, you have this ball here that is made of ultralight reflective walls. So let's say this has very little mass. And I put a bunch of photons that themselves have no mass, and I give these photons a lot of energy. So they're bouncing around in this ball. Then if this ball is not moving, it has no kinetic energy. Okay, but the stuff inside of it has a lot of energy. So we would interpret the energy of this ball just sitting there as a mass for this ball. Okay, so if you have a particle that's made of other smaller things, and those smaller things are moving around, that bigger particle can have a mass from the kinetic energy of its parts. Okay, so not all mass comes from this Higgs field, and this is exactly what happens in the proton. So the proton is made of other things, and almost all the mass of the proton comes from the kinetic energy of these things bouncing around inside the proton. There is some mass that comes from these guys. These quarks have mass, but it's like a percent. So, in fact, most of the mass in the universe is protons, does not come from the Higgs field. It's totally unrelated. Okay, so how does the Higgs field work? As I said, it's the exact same thing as in the water molecule example, but instead we use this V condensate. And the critical difference, or the critical point here, is that this V condensate carries hypercharge. Okay, it has hypercharge 1, right? And that makes our thing consistent. Okay, so now we have this electron that's moving here because it has a mass, it's flipping back and forth, and that's changing the hypercharge. And what we say is that every time it flips back and forth, it interacts with this condensate. So really when it flips back, what's happening is it's absorbing a particle from this condensate. Okay? That particle has this hypercharge 1. This thing has hypercharge 0. So after this interaction, we have hypercharge 1. So that one's conserved. That charge is conserved. Okay? And that's what we say. Every time that this thing flips, it's associated with interactions with this condensate. Okay, and so this brings consistency back to the theory. So we can have an interaction, these interactions that allow mass, and basically what that means is it can go between right and left-handed in a way that conserves charge. Okay, that makes the theory consistent. Okay, now how does it do it? So that was the matter particles. I also said that the force carriers had to be massless. The W and Z have mass. And it's a very similar effect that kicks in to give the mass for the W and the Z. But there's one crucial difference, and that difference is both left and right-handed states of W and Z have hypercharge 0. Okay, so it has to be slightly different. And the way that works is here. So this Z can also flip back and forth if it has a mass. But the way it does it, here it has hypercharge 0. If it interacts with this V condensate, which has hypercharge 1, it's going to pick up hypercharge. So this can't just be the Z again that's pointing the other direction. So there has to be some new particle. Okay, this new particle, I'll write this the omega here. That omega has hypercharge 1 because of conservation of charge here. Now it interacts with this condensate again. It gives off the hypercharge, and now it's pointed in the other direction. So now I can have the Z flipping back and forth with preserving charge at these interactions. Okay, and that's what happens here. So you can see it again. So this is really saying that there has to be a new particle, this new omega. So that's for the Z. It's the same thing for the W. The W is charged. They can have a plus charge or a minus charge. So there has to be two new guys. So it's the same thing, right? It has no hypercharge. It absorbs something from the condensate, turns into something that's new. There has to be two new guys here, because it can be plus or minus. So electric charge has to be conserved. So there's two new omegas. Okay, but it's the same. It's the same trick. Okay, so sometimes these omegas and big omega and small omegas are referred to as the longitudinal polarizations of the W and the Z. So it's a fancy word. It just means it's a new particle that's associated with this W or with this Z. Okay, so that's how these things get mass, and everything is consistent. There's conservation of charge, and these things are allowed to flip back and forth. So I haven't said anything about the Higgs boson, right? I've talked about these omega things. I've talked about this V condensate. So where does the Higgs boson come in? So to see how the Higgs boson is needed, we can ask what's the probability. We have these new fields that exist, right? These new omega fields. We can ask questions like, what happens when they collide? What are the probability for those things to interact? And here's our they have a diagram that looks like this. These things are bosons, so they can all meet at a point. And if we calculated the probability, we would go through put in the factors that are associated with this, the rules that we know. And this gives a prediction that if you would collide these two plus guys, say, you would get a probability that goes like some number times the energy at which they have over the mass of the W. Okay, now this is a problem because when you square this probability, or when you square this amplitude, you have to get a probability. When you square this, so you're going to have some number. Now this, if you go to high energies, this number can be bigger than 1. Okay, and that's fatal. Right now you have a theory that predicts a probability bigger than 1. Again, it's nonsense. We're back to a logical contradiction. And so if you actually put in the correct factors, so if you don't use a squiggle, if you put in an equal sign, then this probability becomes 1 when the energy is like a TeV, so about 1,000 times bigger than a proton. And this is a sign, when this happens, this is the theory telling us that I am breaking down. I do not work at a TeV. So the theory, you can trust it maybe below a TeV, but certainly when you're at a TeV, it's just totally breaking down. And there's clearly something that we're missing when we get to a TeV. Okay, and this is the same theory that predicts all these things, these other things are correct at very high precision. Okay, and what it's missing is the Higgs boson. So this is another thing that's added. So we require a new theory, or a new particle to the theory, just to make probabilities equal to 1. Okay, I'll go through how this works. So it requires there to be a new particle, H, and the one thing we know about H is that it must couple to this W plus. Okay, and actually, if we think more about it, we could have, without going through this probability argument, we could have said that there was a new particle because this H is like a sound wave in the Higgs field condensate. Okay, so it's like an excitation of this condensate that would behave just like a particle, and that's the particle that we found, or that we say is the Higgs boson. Okay, and so now how does this solve our problem? Well, now we go back to this calculation of how these W's scatter, and we have this one that has the bad behavior at high energy, and we have this new diagram, right? There's a new way it could work, and we have to add these together, and when you do this, it exactly cancels the high energy behavior. So now you get a number that's 1, or it's less than 1 for all energies. Okay, so now this fixes the inconsistent behavior of the theory, and we have a theory that's sensible again. Okay, so now I'll just end by saying, so what do we know about the Higgs boson? Just from asking questions of what it is and what does it need to do to get mass, or to solve these problems. So we just said that you can think of the Higgs boson as excitation of this V condensate. Okay, so that means it has to couple to everything. So it has to interact with matter and these W and Z particles, just like these stick figure V's, right? Just like this V, just how they interact with the condensate. So that means we have to have diagrams that look like this. Or remember, we had an electron coming along that could interact with this V condensate and flip spin. And so the Higgs boson must interact with two matter particles like this. And moreover, this coupling strength is related, or how often it flips, is directly related to the mass of the particle. So the Higgs can couple to masses with a probability that goes like the mass of this matter particle. And similarly, it can, remember we had the W and the Z came along and interacted with the Higgs condensate, and it turned into this either omega or omega plus minus. Those we call are identified as part of the W and the Z now. So it has to have this diagram as well. And this coupling has to be directly related to the mass of the W and the Z. Okay, so we know how it has to interact with everything else. That it's totally fixed by requiring that this V condensate is there. Another thing you can ask is, what is the spin of this new particle? Now we know just from quantum mechanics and relativity that the spins are limited. It has to be one of these guys. And the fact that we have these interactions, where you have fermion, fermion, and something has to be a boson, so that removes these two options. So this new particle, this Higgs particle, has to be a boson. And so something I didn't tell you, but it's true, is that when you do the same arguments that say that only these are allowed, say that you can only have one type of spin-2 interaction, okay? And that interaction is gravity, or the graviton. And the fact that the Higgs couples, like the mass, or the fact that the Higgs has a mass and couples according to the mass of the other particles is inconsistent with it being gravity. Gravity couples the same to everybody. So that rules out that it's a spin-2 particle. So we're left with only two options. Now, it could be a spin-1 particle, but this would be kind of weird because the fact that we had this massive spin-1 particle is the whole reason we're in this mess to begin with, right? We had to put in the Higgs condensate to explain how a spin-1 particle had mass. So it could be spin-1, but then we would need another condensate to explain how the Higgs can have mass. Okay, and now this isn't theoretically ruled out, but it would be very bizarre. I mean, of course, it could be Russian dolls all the way down, but it would be strange if it was a spin-1. So just for the sake of simplicity, we say that this is also ruled out. So that leaves one option, spin-0, so it's the only thing left. Okay, in many ways, spin-0 is very weird, and we don't want to have spin-0 particles. Okay, this I'll come back to in a later lecture, but it's forced on us, right? These other things are even worse. And so it turns out that spin particles can have a mass. So you can just say, well, yeah, the spin guy has a mass, and that's totally okay with the theory. But for many reasons, having a spin-0 is bad, but it's forced on us. Okay, so the only thing we don't know, or we didn't know before finding the Higgs, is what is the value of the Higgs mass. We knew it had to have a mass because it's just a pressure wave. It has energy in this condensate, but we didn't know what the value of the mass was. And that's really the only unknown. Everything else is fixed by the fact that there's this condensate, and that condensate is responsible for mass. So it's really here, see, it's not like we have a theory that's making a prediction. It's not saying, well, there should be some new particle. It's saying there should be some new particle. It has to have spin-0, and all these couplings have to be exactly what they are before we even have discovered the particle. So it's really a sharp prediction. Okay, so let's go back to the original statement at the beginning. So this is something that you'll see often in newspapers. The Higgs boson, or God particle, is responsible for all mass in the universe. So it's actually not so wrong. I mean, there's nothing to do with God, right? It's this condensate. It's a sound wave in a condensate. Okay, so no one, scientists don't really call it the God particle. This was introduced to sell books. Okay, there was a book about the Higgs boson, and they thought that it would sell more books if you put God in the title. Okay, so remove that. It's also not the Higgs boson that gives particles mass. It's this Higgs condensate, or the Higgs field, that gives particles mass. And then the other correction to this is that it doesn't give all the mass in the universe, right? Almost all the mass is from protons. It gives some of the mass, okay? Mass of like the electron, mass of the muon and things. But this is very important mass, right? If you go back to the beginning, what sets the scale of an animal goes like 1 over the mass of the electron, not the mass of the proton. So it's only responsible for some of the mass, but this mass is a direct consequence, or has direct consequences for the basic reality. If you would change this mass by a lot, we would no longer exist, or would we exist in a radically different form. Okay, but the original statement is not so far off, and we'll pick up not next week, but in 2 weeks, by explaining what we have to do to verify that this Higgs boson is there. And how we would actually search for it. Okay, so that's all for today.